What does African cosmology have to tell us about the Standard Model of Physics? The Standard Model of Particle Physics proposes 17 elementary particles make up the matter in the known universe. Of these 17, 12 make up observable matter, 4 act either as force carriers which give rise to transformations between the other particles or in one case give rise to the phenomenon of mass. Leaving us with one last particle, the Higgs boson or God particle. We will talk more about that one later. Past, present, future, 1, 2, 3. If you notice, in each of the 3 generations of matter, there are 4 types of fermions, quarks and leptons, being mediated by 4 force carriers. These force carriers or bosons mediate the exchanging of energy, charge, spin, color, etc., between the fermions. There are always 4 forces manipulating 4 particles, meaning there is a 4 by 4 relationship happening here. 4 by 4 plus 1 more. Let's consider the reason there are 17 particles is because there are 4 bosons being applied to 4 fermions in each generation. 4 times 4 equals 16, with one originating source or God particle equaling 17 particles. This description is surprisingly not dissimilar to the Bantu-Kongo depiction of the origin of our universe. On page 27 of Professor Fukia's book, African Cosmology of the Bantu-Kongo, there is an illustration referenced as the Bantu-Kongo mapping of the universe. In this figure, which resembles the depiction of a solar system, there are 3 visible orbits, labeled A, B, and C, and a total of 17 spheres depicted. Whereas with the Bantu-Kongo depiction there is a particle in the center, the standard model chart has the Higgs boson kind of off to the side. This makes sense when you consider it was observed last by modern physicists, and it has some unique properties in comparison to the other particles. If we make one adjustment to the standard model, we see the particles form a pyramidal structure, 2 inverted pyramids actually, seen here in this visualization, and it took a theoretical physicist along with the help of some talented mathematicians and computer scientists over 20 years to develop this very new yet perhaps very old way of viewing physics. Meet in the square. We suggested that moving the Higgs boson to the center of the standard model chart produces a pyramidal structure. The 4 force carriers determine the number of faces for our pyramid. Therefore, the base of our pyramid will be a square. The standard model is square enough, but the particles don't appear to be in quite the right order. When we center the God particle, we get a structure that brings us closer to the base of that 3D rendering we viewed earlier. The 16 signs, Ogdoad e far. A good way to view the Higgs boson, and how it relates to the other particles in the standard model, can be seen in this diagram from a paper entitled The 16 Great Signs and Their Meaning by Medahochi Kofi Omowale. The author refers to this as the primordial matrix. Consider this to be the floor plan for the base of our pyramid. The symbols used on this chart are taken from the African mathematical divination system known as Ogdoad e far. The area in the center of the diagram labeled GBAADU is where the Higgs boson would reside in this model. The 4 corners represent the 4 interactions, strong force, weak force, electromagnetism, and gravity, during each of the 3 generations of matter transformation producing 12 fermions. So are we suggesting that understanding the 16 Ogdoad e far can help us better understand the relationship between the 12 particles of matter and 4 particles of force in the standard model of physics? Yes. Let's take a look at both systems and compare the 2. 12 circles, 4 bars. Within the E-far divination system there are 16 Ogdoad. These are 16 8-bit binary symbols which when squared or multiplied by each other, 16 times 16 equals 256 unique patterns. Each mathematic output is given a name. Of the first 16 binary outputs of the E-far system, 12 begin with an O, fermions, and 4 begin with an I, bosons. Okay, but that's just one instance. Let's get to some real math. Scalar bosons, vector spaces, geometric algebra, metric tensors, gauge theories, etc. Let's start from the beginning. Even if we have these 16 or 17 particles to make everything in the universe, where do we put them? Matter has to exist somewhere. In theoretical physics, the place where matter is observed is called space-time. The scale of particle physics is so small that theoretical physicists have to utilize sets of equations known as Clifford algebras, gauge theories, etc. to map the space-time where the fundamental particles of the standard model can be found. These algebras house complex coefficients relating angles and vectors in a four-dimensional, 4x4, metric tensor usually denoted by G in modern physics equations. For all intents and purposes, a metric tensor is just a four-dimensional manifold, x, y, z, t, where t represents time. More math. In 2013, Alamu Femi, a PhD, a lecturer and researcher at the Department of Computer Sciences, University of Lagos, published a comparative study on IFA divination and computer science. In it, the scientists make the following statement. Over 12,000 years ago, Africans developed IFA oracle divination based on the square of 16 equals 16 times 16 equals 256 equals 2 to the power of 8, corresponding to the vertices of an 8-dimensional hypercube and to the binary two-choice Clifford algebra C1, 8. The processes used in IFA divination and the divination system bear some similarities with computer science. Also, computer science takes its origin from IFA divination. The math necessary to produce 16 particles in space-time is also the math necessary to produce the very space-time those particles exist in. Meaning that not only can IFA be an epistemological tool to help us remember and understand the relationships between the particles of the standard model, but it may also be a key to understanding the geometric algebras used to map space-time itself. The geometric algebras required to chart space-time are not only present in IFA, but are at the very heart of the African mathematical system. 4x4, metric tensor. In general relativity, a point is an event with both a location and a time. Four-dimensional vectors, or four vectors, are required in general relativity, and these four dimensions are length, height, width, and time. When squared, they produce a 16-component grid used to chart any event in spacetime. When plotting points in general relativity, mathematicians use 10 of these 16 components, 4 lines, dimensions, and 6 angles of arc to plot points in space, the other 6 angles being used as coefficients to determine the shape of spacetime. Hip-hop aficionados may notice a similarity to Grandmaster Flash's quick mix theory, 4 bars forward equals 6 counterclockwise revolutions, published in 2017. After all, Grandmaster Flash did study as an electrical engineer at Samuel Gompers Technical High School in the Bronx. I wonder if he knew anything about the metric tensor when he discovered the QMT in 1973. I can hear you asking, well, how does that get us to the 3D model we saw earlier? Looking at a square does not get us to a pyramid, or does it? We have to remember the square we are looking at is called the metric tensor, and it is 3 dimensions of space and 1 of time. We can place our mind's eye anywhere in time and space, including the top of a 3-dimensional pyramid. Chris Quigg, a particle physicist at the Fermi National Accelerator Laboratory in Illinois, describes this visualization as a double simplex representation, because the left-handed and right-handed particles of nature each form a simplex, a generalization of a triangle. If you take into account that those triangles are in 4D space, they actually form pyramidal structures, 2 of them in fact joined together to form a figure 8 or infinity-like structure with the Higgs boson as the central capstone of each pyramid. Symmetry, duality, balance, polarity are always present in the natural world. These symmetries may not always show up where scientists expect to find them, but they are always there in a system where energy and matter are always conserved, E equals mc squared, and the loss in that system is none, Gij, J equals 0.